Hello. This segment is going to be focused on graphing trigonometric functions and their transformations. My name is Melody Elrod, and this is one in a series of videos on graphing trigonometric functions and doing trigonometry in general. If you haven't already, you might want to peruse through my channel to see if you need a little refresher on building a unit circle, building right triangles, or graphing trigonometric functions as parent functions as well. So let's go ahead and get started. You'll remember from the first video, the parent function video, that the graphs of sine x and cosine x look a little bit like this. And we're going to refer back to these just a little bit as we move through the video. The first thing I want to talk to you about with transforming trig functions is their attributes. The attributes of trig functions, there are four main ones that we're going to talk about today. The first one is the period. The period of a trig function is how long it takes for that the x distance required for that trig function to repeat. And this is what I mean by that. So let's suppose we have the cosine of x. Okay, how long does it take for this function to repeat? Well, it starts here at 0. The x value is 0. Pardon me. The x value is 0 here, and then it goes all the way to 2 pi before you find that same value again, and it begins to repeat itself. So this x distance is 2 pi before it repeats itself. Okay. The second attribute that I want to talk about with you is the amplitude. The amplitude is the y distance that is possible from the middle. So what that means is this. So let's go back and look at our cosine again. So the value, the distance, the y distance now, so vertical distance from the middle. Here's our middle line. Our middle line goes straight across the x-axis normally. So here's our middle line. And the function, you can see, can only go one up or one down at its maximum. And so the amplitude of a normal parent cosine function is just 1. And so those are two of the main attributes. Looking at the next attributes of trig functions, we find the phase shift, which is where the period begins, the x value where that period begins. So we know that on a parent graph, it normally takes 2 pi for it to repeat itself. Let's look and see where that normally begins. So here's a sine graph, not a cosine graph. So on a sine graph, again, it takes us from here all the way to here to begin to repeat ourselves. It takes a full 2 pi to repeat ourselves, and that begins at 0. X equals 0 is our normal or parent phase shift. Let's call that the parent phase shift. It's the default, if you will. Those of you who are tech savvy know that things come with default settings. So if we don't do anything to our trig functions and we're dealing with them only in their parent functions, that would be the default setting for where a period begins. All right, so we have the phase shift, and then the next attribute is the vertical shift. That would be the y value where the midline is situated. Where is the midline? So we've already discussed that on the cosine function, but on the sine function we can see the same thing is happening, that for a parent function, the midline is y equals 0. So y equals 0 is our midline. Okay, so that would be the vertical shift. This would be the parent vertical shift. Okay, so those attributes. So what does that actually mean? Well, let's talk about them more specifically. Let's talk about the domain attributes, the ones that have to do with the x values, and those would be the period and the phase shift. So what do we do with these values? Okay, so normally a period begins at 0. We just discussed that. And has a distance, an x distance of 2 pi before it begins to repeat itself. So here's our period, and here is our phase shift. And so we can notate that this way. We can say that the input value, for example, in sine of x, x is our input value, runs from 0 to 2 pi. So for example, suppose we had this. Suppose we have y equals 4 times the sine of 3x minus pi minus 2. So what does that say about the period and the phase shift? Well, if we know that the input normally lies between 0 and 2 pi, what we need to ask ourselves is, what is the input? The input in this particular case is 3x minus pi. That is what we are putting into the sine function to find a value. So we're going to say 3x minus pi runs from 0 to 2 pi. If we solve this for x, we can actually figure out what the new period and phase shift are for this transformed sine function. So let's add pi to all three sides, as it were. And let's divide everything by 3. And so here we go. So now we know, okay, so this tells us a couple of things. Let's identify what we really have here. Here is our phase shift. Okay, the x distance that it takes to begin the period and end the period is going to go from pi over 3 to pi. So what we need to do is to figure out what that distance is. So we're just going to simply subtract. 1 minus a third is 2/3. So 2 pi over 3 is our period. Now, if you're watching this video after reading a book on trigonometry or listening to a professor talk about trigonometry or having a classmate help you with trigonometry, this may not be the way that they told you to find the period and the phase shift. But I challenge you to go back and use both methods that you've learned and see if they don't give you the very same results. And then I encourage you to discover which one makes the most sense to you, which one is the simplest for you to execute, and to adopt that one and to use it wholeheartedly. Both of these are sound mathematical ways of doing so, the way that I'm showing you here. And the formula way, I'm not going to go through the formula way here because I don't want to present competing methods here. But if you've learned a formulaic way of finding the period and the phase shift and it works for you and it makes sense to you, then I encourage you to continue using that. It's not that one of them is right and one is wrong. It's simply two approaches to the same ends. All right, so let's continue on our talk, and let's talk about the range attributes. So those would be the amplitude and the vertical shift. Those are the ones that have to do with the y values. Normally, the amplitude is found, is 1, right? We normally only go 1 from the midline. And the midline itself is usually y equals 0. So we can notate that this way, that the output, the range values, right? So the range, or if we were using just the parent function, sine x itself, usually runs from -1 to 1, where the midline is the midpoint of those two. It's halfway between -1 and 1. So let's do an example. What does that mean for the example that we just had? So suppose we have, again, this 4 times sine of 3x minus pi minus 2. What does that say about the amplitude and the vertical shift? So here we go. So the output runs normally between -1 and 1. If we want the sine of 3x minus pi, to turn into 4 times the sine of 3x minus pi minus 2, then here's what we need to do. We need to multiply by 4. So we multiply by 4 here. We multiply by 4 here and here. Okay, so that's just expanded our range. And then we have to shift that range by subtracting 2 everywhere. So 4 times sine of 3x minus pi minus 2 will be 4 minus 2 and negative 4 minus 2. And so here is where our range is. So our amplitudes, okay, are going to run from negative 6 to 2, where the midline is halfway between those. So the midline is going to be the average of the two. Remember, the easiest way to find a midpoint is to simply average the two endpoints. So if I take negative 6 and 2, and I average them, then I get negative 4 over 2, which is negative 2. So the midline would be at y equal negative 2. Okay, so that's a lot of information to take in so far. Let's see what we can do with that. So, now what? How does this change the graph? So let's start by reminding ourselves how we drew the graph of sine x to begin with. So here's y equals sine of x. We know that we have to know what the y scale is, that it's going to go up to 1 and down to negative 1. And we know that there are these 5 key points within one period. There's the beginning of the period, and then there's 1, 2, 3, 4 points that represent, if you remember, that represent the 4 quadrant angles in the unit circle. In fact, let's look at those real quick. So here's my unit circle. Remember, the 4 quadrant angles are 0, pi over 2, pi, 3 pi over 2, and then back to 2 pi, right? Because that's the same as 0. So these 5 key points is what our graph is normally based on. So here we've got pi over 2, pi, 3 pi over 2, and then the same in the negative if we want to do it both directions. Okay, I'm only going to worry about one period for right now. So this period, the period is split up into 4 pieces to represent the quadrant angles, right? So, and then we know that the sine, the general behavior of the sine is that it begins at 0. The sine value is 0 at 0. It's 1 at the first quadrant angle, back to 0. It's negative 1 at the third. And then it's back to 0 at a full rotation. And so here is my sine curve. So how is that going to change things when I look at the example problem that we were just doing? So let's graph this example and see what happens. I'm going to make my pen just a little bit smaller so I can do a little bit more fine work here. Okay, so we know that the period in this particular case is 2 pi over 3, right? We found that in one of the previous examples. We know that the amplitude is going to run from negative 6 to 2, right? Which is actually an amplitude of 4 away from the midline. That the vertical shift was at y equals negative 2, that's where our midline was, and that our phase shift was at x equals pi over 3. All of those pieces of information, if you've been taking notes on this particular video, should be on your page by now. You should have this information. So let's make this happen. Let's figure out how we're going to graph this guy. So we know that we need to run from pi over 3 to pi, right? That it was going to go from pi over 3 to pi. That's how we figured out our period and our phase shift. And we need to cut this into 4 pieces. We need to divide our period into 4 pieces. So hopefully you're familiar with the idea that dividing by 4 is the same thing as multiplying by a fourth, which is sometimes easier to do. And so we end up with pi over 6 as our increment here. So we're going to start at pi over 3. We're going to add pi over 6 to that. So we'll end up at, so pi over 3 is 2 6, so we've got 3 6 and 4 6 and 5 6. And then the final 6 6, because what is 6 over 6? It's just pi, right? So there we go. We know that we're going to We're also going to have to shift our midline. So let's choose a different color here, just so that we can see our midline a little bit more easily. I'm going to draw in a line. We'll call this -2. Okay, so we're going to just give ourselves a little midline. Now this is not actually part of the graph. This is just for notation. So here is -2, whoops, on the y scale. Let's try that again. Okay, we know we need to go down to -6 and up to +2. Okay, that was our y scale. So now we have all of the tools that we need. We have our x scale, our y scale, the increments for both. Everything's cool. So we're going to go ahead and use the behavior of sine. Sine begins at the midline, at the starting point. Now, this is the tricky part. Everybody wants this to start right here on the x-axis because that's where it's supposed to start. But that's not true because we had a phase shift that shifts it over to pi/3. And so we've got pi/3 up to 2 at 3 pi/6 or pi/2. Back down to the midline, back down to the minimum, up to the midline, and here's the general shape of our curve. Now we could go through and do 2 periods if we wanted to. All we'd have to do is continue this pi/6 thing, right? So it should go down to pi/6 and back up to 0, and and back and forth we go. In fact, I didn't quite give myself enough room right here to make that happen, which you could explore further and find for yourself. But here's the general graph of this curve. This is what this is going to look like. So hopefully this has been helpful to you in figuring out what to do with transformations of trigonometric functions. I encourage you to go through and find some other examples and try some things on your own. You can find other things online, or you can go to your textbook. You're also welcome to shoot me an email if you have questions. So this will end us here. So I thank you for watching. There will be another video in this series, more than likely, that deals with how this manifests in the graphs of cosecant and secant, the graph of cotangent and tangent, though they're very similar to what we've done here. So there'll be a follow-up video coming later on, but hopefully this has been helpful to you. As always, if you have questions, feel free to visit me at melodyelrod.com or shoot me an email. Have a great day.